Thanks, Laura and Thomas, for organizing this workshop. Thanks to the audience for being here. And thanks again to Laura and to Daniel for preparing things. Another version of this talk could be, how can volume conduction screw up our estimates of brain connectivity? Basically, it's an exciting new field measuring functional connectivity in the brain. And it's very recent. Oh, oops. It was already done in the 60s by Livanov. This was done actually by using mechanical calculation, and it just shows the correlation between electrodes when a person is resting and when a person is doing mathematics. And here already we have the question, does this reflect the brain? What is it that it means to talk about a functional and effective connectivity? So I'll talk about the problems, but I'm going to first hammer in some ideas. Here is a more modern version. I actually did this. This is the imaginary coherence for 60 electrodes in a person with resting state. And one of my students had fun, went into the graph theory, came out with small world things. Is this interesting? Well, I don't think so, and I'll show why. Then, what is going to be my talk? I'm going to talk about the effective brain connectome, why we formulate the effective brain connectome as a state space model. Are there magical measures that allow us to ignore volume conduction? And then, does this situation change when we find previously independent components or other type of components? What would be the ground truth, and what are some of the remaining challenges? So quickly, this is to hammer in, we have to have common terminology. Effective connectivity comes from anatomical connectivity. If we have one neural mass, another neural mass, they're directly connected by a group of axons. That anatomical connectivity becomes an effective connectivity when activation of this drives causally the one-link connection. If we have indirect connections, or we have somebody outside and we see correlation between one neural mass and the other, like this here and here, that's functional connectivity. This is Carl Friston's definition. I think we should adhere to it. If that's so, functional connectivity is just correlation. We're not interested in that. I mean, it is an intermediate step, but what we have in our minds is that we want to look at effective connectivity, and we may not reach it, but we should distinguish both things. So talking about, as I've seen in some papers, let's measure the effective connectivity amongst the scalp electrodes is nonsense, because the electrodes are not neural masses. There's no axons between the electrodes. We're inferring something that's hidden. Now, I have a formal definition. I threw this out at the brain connectivity workshop of what the effective brain connectivity is. And for me, it's a graph, but a special type of graph. It is the set of all possible activations. This is the Cartesian products. We're looking at all pairs, plus delays. And that maps on to a measure of information flow. And Daniel has expressed this. Now, this would be then the effective brain network graph. We're measuring activity at nodes, which can be either points, neural masses, or manifolds. They can be neural fields. But we have delay, and this is something that the fMRI guys, since they can't measure delays very well, they ignore it. But we in EEG have the advantage that we can put it in. And of course, this is any of the information measures that in general were defined by Biener, Akaike, Granger, Schroeder, and Laura has expressed it. People tend to forget some of the other guys, but they had equivalent definitions and base that could be traced back to the transfer entropy. Now, as Laura's shown us, if we have here, this is the graph I'm going to be using, we have two neural masses, each influences itself over time, and there can be cross-influence. And this is the expression, which is exactly with just a different notation of what Laura did. What is Granger non-causality? It's simply a link that's missing. You cannot predict, or this two, for example, here does not increase the possibility of prediction one. Now, this is the basis of all you can have an information formulation of this, you can have nonlinear formulations, But let's keep to this because the essential points can be brought out. What happens when you have N sensors, a bunch of sensors? Well, then you need to have a large matrix which will describe the effect at a previous time on a future time of any neural mass. And that can happen for several delays. So here I've put just 2 delays. We have these 2 out of regressive matrices. This is lag 1, this is lag 2. That actually corresponds to delays in time. Now, this stresses the point that when we're looking at an autoregressive model or in general effective connectivity, we're looking at the Cartesian product, the set of all pairs of points in the brain to points in the brain. And this matrix that I'm just taking 1 lag, any column, as Laura explained, is simply what is the influence of any given point here, which would be a point here, on other places. So we can say that the columns represent what is the effect, the outfield, and the rows is the infield. That is to say, what is the influence in a single point of any other point. Now, something I want to stress is the following. If we have several autoregressive models, and I'm summarizing here the whole situation. So here we have the vector at time t. These are past vectors. This is the driving innovation. And here we have the autoregressive coefficients that represent effects at lags. They can be viewed as a multidimensional array. That is to say, a tensor. And one of the things I want to stress is that we must be using more and more tensors. A way to represent multidimensional tensors is that we can use the Penrose diagrams in which we have a node which can be either a circle if it's a variable, or it can be a square if it's a constant, and then have the number of lines departing from it tell us what is the dimensionality of this multidimensional array. Viewed like this, what is effective connectivity? It is simply a tensor that goes from the emitters to the receivers with a certain delay, and it tells us how information is flowing there. The support of this, where these guys are not 0, is this hypergraph, and this hypergraph is simply the Cartesian product, which has to be its structure, its underlying is the structural connector. So that's a definition that we keep in mind. Now we go to see why we have to see it as a state space model. We have anatomical connectivity, as I told you, that produces effective connectivity when neurons fire. These then produce functional connectivity, which is that we're just measuring correlation, and what I call correlation functional connectivity. Now, we do all of these, or all these measurements are not seen linearly. We don't observe them exactly. We have imperfect knowledge. Therefore, we have to estimate the anatomical connectivity, the effective connectivity, and the functional connectivity. And here's where functional connectivity has a reivindication, because we usually proceed of measures of functional connectivity that then narrow down to effective, and actually, we have to combine all types of information. So what we really have is the following. We have our state space model. Let's say it's going to be a linear state space model. We're going to be based on the multivariate regressive model. And this will describe how narrow states at any given previous time will influence future states. And here we have the elements of the connectivity tensor, the autoregressive tensor. But then we have to add on to this an observation matrix. That is to say, these activities phi t will be modulated through the lead field and give us voltages that we're going to measure, plus additional noise. So here we have innovation, which is actually a driving force. This is sensor noise. Now, if we have this, we can look at it this way. We have here the dynamics of this multidimensional system. This is the number of sources. Each of them has its internal dynamics, which is expressed by the diagonal of the autoregressive matrices, but we also have the cross terms that is the influence of any given neural mass on another. And then these guys project by volume conduction to our sensors. We have an observation equation again, and we have then the state transition equation. Now, many people, one would say that one should estimate the connectivities and the states from the observations, you know? That is to say, we want to estimate actually the state evolution equation from the data. But people that believe in magical measures say, oh, we can eliminate completely the estimation of this. We can go directly from the voltages to the connectivities. So what they're saying is that we can infer this from this. And I'm putting it quite crudely. Let me give some examples. And before that, I have to say that one of the most common examples is that people say, measure X is immune to volume conduction. And to put the name, directed transfer function is immune to volume conduction. And it's based on really artificial arguments that if we separate a single frequency, then what appears by volume conductions has zero lag, and things that are lagged, presto, they will not be affected by volume conduction. Now, these two papers, one by the group at the Schwartz Center, the other is Frederick van der Steen, Daniel Marinazo. Here, they examined this situation. And first, a theoretical argument. This is what we have in the state space. This is what we have in the observation. Let's take this and plug it in here. That is to say, that implies that any given voltage is the lead field, and we're going to have the autoregressive model. So we're going to have all the mixing of connectivities, but we're going to have this guy that's the lead field here. Of course, the lead field will also affect the noise. Now, the question is, can anybody in his right mind believe that we can get measures of this guy without taking the lead field into consideration? I just look at the formulas, okay? It really takes magical thinking. If anybody argues that there's a measure that does not take the lead field into consideration, that is to say, that does not solve the inverse problem, then I do not believe it. So I've combined these two noises into here, and here is an example from the paper by Frederick van der Steen, and here we see the connectivity of several sources. Here we have two in particular. This is the true connectivity in the frequency domain, and what we have here is doing the inverse solution and then finding the connectivity. This is source space estimation of the directed transfer function, and we have, this is the source reconstruction in cyan, and then sensor space in yellow. We can see that there's false positives, and it's not surprising. I only have to look at the math to notice this. I have to mention that people sometimes come forth and say, this is the new measure that will eliminate the need for looking at the lead field. And they put one or two examples. Unfortunately, isolated examples don't prove a general point. But a single counterexample, which can be done by simulation, can refute. So my message is mistrust any measure which claims to be looking at brain connectivity directly and does not take into consideration the lead field. Now, another idea, which is a total misconception, is the use of imaginary coherence. And it is based on what I call the phase fallacy. So the idea of the phase fallacy is that if you have a lagged direction of interaction between two neural sources, and you're then looking at sensor space, because there's a lag here, the imaginary part of the Fourier transform will not be affected by volume conduction. So this is a very simple argument, okay? Phases reflect delays. When you have a complex number, you have a real and imaginary part. The real part can be affected by volume conduction, the imaginary not. This is not what Guido Nolte said. He's never said this. In fact, let's look at the formulas. Here we have what is the model I was explaining. So here we have the effects of the autoregressive model, which depends on the pasts and the directions. You have the lead field. You transform it to the frequency domain, and here I'm using a notation similar to that used by Lauda. You have not gotten rid at any point of the lead field. And this is simply very similar to the expression that Lauda gave us. Now, if we now look and take the imaginary part of this expression, we have the lead field multiplying the imaginary part of this transfer function multiplied by the actual sources. And then, of course, the imaginary part of the noise. Once again, how can anybody say that by taking the imaginary part of anything, you can get rid of volume conduction? This is one of the examples of the urban myths that arrive out of incorrect interpretations of serious work like that of Guido. What Guido demonstrated is that if you have independent sources on the scalp, the imaginary part will be, the coherence will be 0. Now, a guy a few years ago, Aristoteles, showed that when A implies B, that does not mean that B implies A. And that's what people are doing. So, what does the situation change by finding components? No. And this is something. I'm going to be looking at rhythms now, the alpha rhythm. This was something we published using sparse source localization of the spectra in 1996. And essentially, what we're going to apply to that is a decomposition. You know that decompositions or components is taking data that's a matrix and then decomposing it into, in our case, if we have space and time, into spatial and temporal signatures, or spatial and frequency signatures. A prime example which has inspired us all is independent component analysis. I'm just taking from one of Scott's lectures the idea that you can decompose, not by using principal components, which is then subject to arbitrary rotations, but by imposing independence, and he's argued eloquently for this approach. You can decompose a resting state alpha rhythm into components, and then you can carry out the sort of source localization. We have an approach we think is complementary, because what Scott does is he does independent components and then finds the sources. I think we can do both at the same time. So what we're proposing is to do an independent component analysis on the sources, and the way we do that is by requiring that the sources be spatially independent. Mathematically, you can do that by saying that the spatial distribution of the sources has to be non-negative and orthogonal. And here we tie in with all that literature on non-negative matrix factorization. And essentially, what it does is that the alpha rhythm is decomposed into several different components. We can elaborate on this using the tensor nature of EEG data, which is space, that is to say derivation, time, and frequency. Here we see the fluctuations of the alpha rhythm. And using a decomposition, you can look up in our proceedings of the IEEE review, you can now take these sources and see both the differential spectra, but also the fluctuation of their temporal signatures or strengths. And the point I want to make here is, here's the data I was showing you at the beginning of the talk. This is the stuff that my students had fun passing through all these hub programs and, graph theory. And actually, the explanation is really very simple. There's an alternative explanation from our analysis that there's just 3 little sources here that don't have a complicated structure. So once again, when you're dealing with EEG or MEG, beware of ignoring the lead field, because it can introduce entertaining but totally useless information. Now, what would be the background truth? I think we started seeing from Scott's presentation, it is simultaneous recordings. So the ground truth, first, one of the problems we have to face is that we have to solve a large multidimensional problem. And I have to admit that there's leakage, there's a number of problems with finding problems of connectivity in the inverse solution. But these problems have to be addressed. Saying that the problems exist does not mean that we will stick to the sensor space. And one of the important things is that we have to solve both equations simultaneously. What we usually do is to solve the inverse problem, that's what we've heard a lot today, and then look at trying to estimate connectivities. A better approach, which I don't have time to go into, is to actually solve the state space equation as we stated a number of decades ago. And in fact, there's work going on in this direction, but it's challenging because methods like the Kalman filter, they really break down when you have high-dimensional time series. Okay, the ground truth. Data like from humans, or this is a data set we've put out there for people to analyze. This admittedly is still missing because we have 128 electrocardiogram. This is data recorded by Naotaka Fuji at Riken. It's available at Neurotycho. We've cleaned it up and calculated the lead field. So you have on one hemisphere ECOG, and then you have the 10, everything was put together again, and then the 1020 system. We suggest that this analysis be done, but it brings up an important point. This is how the activity changes over time. And I have to say that it brings up the point, and this is not measuring in volume of conduction like the movie that Scott showed us. This is the actual data. So how much of this are discrete generators that are transmitting information to each other? How much is there wave propagation? I have to say that this data is an excellent correspondence, the EEG data with the ECOG data. Here you can see a complex valued CCA, a canonical correlation analysis between the external data and that on the cortex, and you can see a number of canonical spectra, and they are all very significant. This is the significance level. So there's promising work to do that. This data is publicly available, and in fact, with Christoph, we have launched a special issue that's still open to analyze data like this for the controversies in EEG. Now, what are some of the remaining challenges? Well, one, it was improving the source connectivity. I already spoke about that. Another is dealing between the dichotomy between wave phenomena and localized phenomena. A number of years ago, we proposed decomposing the EEG. This is work when Roberto Pascual was doing his PhD at the Cuban Neuroscience Center. And what we did was that we do not believe in band analysis. And Christoph, maybe this is the reason that some of the results don't hold up, because you have a 1/F activity that cross-cut all frequency bands. And then you have localized peaks. And it is precisely these localized peaks that are real rhythms, because we have to distinguish between an EEG rhythm and activity in a frequency band. And what we found a number of years ago, this is from the 90s, was that if you did principal component analysis of hundreds of subjects, in this case 300 subjects, you came up with essentially a number of components that looked very much like the spherical harmonics. What are the spherical harmonics? The spherical harmonics are the Fourier transform on the sphere. And it is quite interesting. You can see here, these are the principal components from 300 subjects of the EEG. Below is the spherical harmonics, and we've ordered them so they are most similar, no? But the similarity is striking. Moreover, at that time, we had a lot of discussions, but this is an unsettled issue, that these look like the microstates, okay? So maybe these, now, is this just due to volume conduction? We all know that a spherical model of the head, the lead field, can be expanded in spherical harmonics. I don't think so, because there's also a lot of evidence now that narrow fields can decompose into spherical harmonics. This is just one paper. There's several others coming out. So what can one speculate about this? Wave phenomena can be described by spherical harmonics of narrow fields. They pass through something that can also be expressed, the lead field, approximately as with spherical harmonics. I would say it's not surprising that some of the activity that gets out there looks like spherical harmonics. Could this be the basis of the microstates? I don't know. That's a question that I'm launching here. I do want to mention that with Thomas Koenig a number of years ago, we tried to pose the frequency space and time evolution of microstates as an inverse problem. There's an interesting paper out there, and this is my tribute to Dietrich, who really was an inspirer of all of us. Now, can we reconcile, for example, in this case, we have alpha activity that corresponds to several microstates. How can we look at the pictures I gave you of localized activity and wave activity? When one way we tried to do this was by taking Paul's Nunes theory and then looking at propagation of waves in different band lengths. And this is the mathematics. I can send it to you later. But the interesting thing here is the following. When you do a realistic simulation of the propagation of alpha activity, let's see if this works, well, it doesn't work, but I'll tell you what it does. Instead of there being widespread waves, the activity of the alpha dies out rapidly. So it can be described as a wave phenomena, but it is a wave phenomena that has very rapid damping. So there's a duality between wave activity and localization, but there may be a middle ground where everything depends on the damping factor of the waves we're looking at. Finally, I want to say that a lot of these opinions have been expressed in this review that Laura was kind enough to mention, that was done with Allard Robrek, with John Daniso and Carl Friston. This is the 2011, where we clearly state that we think that effective brain connectivity has to be done within the framework of a state space model. And that state space model, specification and testing, requires a number of steps which we outline here. So for those that are interested, this is some of the papers, and these are the collaborators over the years. And I just want to mention that we have recently created the Cuba-China-Canada Alliance. Bharat Biswal is joining us there. And as the final ad, that we're looking and recruiting for people to try to help us answer some of the questions I've posed. So thank you.
Okay, we are at the end of the talks of this morning, but we still have some time for questions that may have come up. Are the questions, is somebody having a question that we should address in the plenary now? Yes, otherwise you can also address the speakers directly. We are around all day. Okay? So have a good appetite, and we are back at 1.